Hello, my name is Victor Villanueva, and welcome to my presentation on my project titled Quantitative Mental Graphic Analysis Using Machine Learning. Before we get started, I would like to thank my sponsors, them being the Center for Research Excellence on Dynamically Deformed Solids, CREDS, supported by the U.S. Department of Energy under the National Nuclear Security Administration, as well as the Texas A&M University OREU program. And I would also like to thank my collaborators, which are Professor Ankit Srivastava, as well as graduate students Becca Sil and Lara. Now going to the motivation for this project, our motivation is understanding material failure is essential to avoid costly and catastrophic outcomes. As shown to the right in this image of a broken plane landing gear, material failure can cause enormous cost as well as enormous risk on human life. And so understanding what causes materials to fail as well as knowing how to prevent failure from happening is very important. And so failure analysis is the process that allows us to determine what caused the material to fail, as well as how it specifically failed and where in the part it failed. And as we will learn, this process, although it is being used today, it is still primarily qualitative in its use. So going into how failure analysis is conducted, there are two regions that I would like to highlight. They are ductile regions and brittle regions. Starting with ductile regions, they are characterized by their rough appearance, such as up here and in the middle here. And so ductility is caused by voids populating in the sample. And so voids are essentially empty space that grow as stress is applied. So they grow. And as the void expands, it is growing empty space within the material. And if it grows too big, it will coalesce with other voids, and these voids can cause separation of a part, causing failure. And the other region in this image are the rest of these smooth looking parts of the image, and this smoothness is characteristics of brittle regions. And so brittle regions are caused by unstable crack propagation. And so these are when there is a separation present in the material, and if there's nothing to stop the separation from happening, it will suddenly propagate through the material, and the material will fail through a crack. And so, as you can see, just by looking at this image, we can learn about the different types of failure and what may have occurred to cause this surface, but there is no quantitative data. And so our project goal is to create a machine learning pipeline to provide quantitative analysis of fracture surfaces. So going into the specific goals, there are two goals for this project. One is to create a data set of annotated images, which I will show examples of later, and then to use these images to train a machine learning model to identify ductile regions. To do the annotations, I will be using the LabKit plugin of ImageJ, and ImageJ was chosen because of its ease of use, it being free, it having a high quality zoom feature, as well as it being able to save file types, any file type that you want, such as PNG and JPEG, which is important for this model to work. And going into the machine learning model itself, it will be using the UNet deep learning architecture for semantic segmentation using the TensorFlow library. And so going into the model itself, we can see the U shape, hence the name UNet. And so explaining how the model works, we input the image up here, and it goes through the encoder portion of the architecture where it goes through convolutions, which is each of these. And at each convolution, the image is essentially contracted. And at each contraction, the model learns more details about what is present in the image. And once it gets to the smallest contraction possible, it goes through the decoder, where it goes through the same amount of expansions instead of contractions. And as it expands, it gets more information on where the specific classes are located within the image, and it outputs a segmentation map which highlights the different classes located in the image provided. And so Python and Google Colab were used to build and run the model that is shown here. And so going into fracture surfaces that are present in our project, the fracture surfaces that I have been showing images of and the ones that we use for our data sets were created by tensile testing HY80 Steel. And 32 images were created for training, validation, and testing of the model. And it must be noted that data augmentation techniques were used to create more images because 32 images on its own is not enough for a machine learning model to learn and to provide analysis. And once again, we are learning for the fraction of ductile regions on these steel surfaces, so these rough areas here and here. And it must be noted that expert knowledge of fracture surfaces is needed for accurate image annotation. Someone that has limited experience on looking at these type of fracture surfaces will incorrectly annotate these images, and incorrect annotations will cause the machine learning model to learn wrong information and cause discrepancies in the accuracy of the machine learning model. So here I show examples of the training process that I used in ImageJ. So this is the original starting image, and this in the middle is the annotated image within ImageJ, and these green regions are ductal regions that I want the model to learn. And on the right is the exported image, where this is the image that I am exporting to the machine learning model, where white is the ductal region, and this image is what the machine learning model will use to learn what is ductal and what is not when paired with the original image. And so going to some specific results of the machine learning model, these are original images. These are ground truths, which are images that I annotated. So in this example, the ductal regions are these dark regions or purple regions, and the yellow is non-ductal. And the model prediction is, as the name suggests, what the model predicted this image to look like. And so just visually, it is giving favorable results. As we see, there are a lot of similarities. And going into the quantitative part of the results, I used Python to calculate the ductal region percentage of the fracture surface using the libraries of NumPy and OpenCV. So going back to the numbers, I labeled these number 1 and number 2. I calculated the area on the ground truth, which is real area, and the ductal area of the predicted image, and in order to calculate the amount of ductility present in each of these images. And this can be used if, let's say, there are two different samples of these metals to see if there was a loss of ductility due to some processing or effects of environment. And also in the quantitative section, we would like to see how accurate our model is being. So there are two methods that we came up with to measure the model accuracy, which are area percent error and the F-score. Area percent error is easily explained. You just calculate the ductal area in the ground truth and the ductal area in the model prediction, and you compare them by doing the percent error calculation, which is done here. And the lower the percent error, the better your model is doing theoretically. And the other way is the F-score, which the process is shown visually here, where we take 2 times the area of overlap, pixel overlap in these two images, divide that over by the total amount of pixels in both images. And this will give us a number, and examples are shown here of the calculation. And the perfect F-score would be 1 because there would be perfect overlap, which would be 1 divided by 1. So perfect is 1, and a no overlap F-score would be 0. And so it must be noted that F-score is a better metric for accuracy because of its use of this overlap feature in its calculation, because percent error, your machine learning model could have low percent error, but it could be annotating the same amount of ductility in the ground truth as the model prediction, but they could be in completely different locations. And so your model isn't doing a good job. And so F-score is a good way of calculating accuracy of your model because it takes into account whether they are actually overlapping or not, as well as the total amount of pixels in both images. This is shown clearly here as number 1 has high percent error, but also the higher F-score. So if we were using just the percent error, we would say that it was less accurate, but in reality, it was the more accurate prediction of the two examples. And it is also commonly shown that F-score is a good measure of average performance of the model. And so in the end, we set out to get 2 goals in this project. The first goal was to create a data set of labeled images, and the second goal was to train the model, a machine learning model, on these labeled images to identify ductal regions. And so judging by our results, we can say that we accomplished these goals, as well as the images shown earlier, and as well as these 2 images, for example. And going through 10 random images, I calculated the average percent error and the average F-score, and seeing these values, they are not the best, but there is room for improvement. And so in the future, if we were to do this again, we would suggest using a larger data set than the 32 images that we use, plus the data augmentation that we did. And so a larger data set would provide ample opportunity for the model to learn on its own and correct its mistakes and make sure that it is annotating more areas that are ductal that actually are ductal rather than areas that aren't. As well as in the future, there may be an improved deep learning model to the UNet architecture that may be more accurate, as well as there may be more efficient and more robust data augmentation techniques, because in material science, currently there is a limited amount of training data sets available to us. And so data augmentation is very important at the moment. And so increased efficiency and effectiveness of data augmentation would be very helpful in scenarios like this project. Thank you for watching this video on my project.